In these circuits, the bulbs have a resistance of 1 ohm. Let's assume that they're matched bulbs. And every cell has a long positive terminal and a short negative terminal, and those are worth 1.5 volts each. Now in Kirchhoff's loop law, the total potential change in an entire loop has to be 0. Every time we go from a negative plate to a positive plate, though, we're going to be adding 1.5 volts. And whenever we stack batteries in series like this, we just keep raising the potential with every battery. So this is going to be a total of 4.5 volts at this point. Assuming that we designate the negative terminal as 0 volts. We want to be able to label the potential values at different points around the circuit, and we want to compare the brightnesses of the bulbs in these situations, and we'll see how stacking batteries in series and and putting them in parallel, how does that affect the brightness of the bulbs. So in order for the sum of all the potential changes in the loop to equal 0, now what's going to happen is we're going to lose 1.5 volts in the first bulb, 1.5 volts in the second bulb, and 1.5 volts in the third bulb. To prove that this is true, let's find the equivalent resistance of the entire circuit. We've got a 4.5 volt battery, and we want to simplify our bulbs to just one equivalent resistor. Because our bulbs are in series, the equivalent resistance is going to be the sum of them, so it's going to be 3 ohms. This will allow us to find the current through the equivalent resistor, because we'll divide the total delta V of the battery by the resistance of the equivalent resistor. So that's going to be 4.5 volts over 3 ohms, and it's 1.5 amps. Alright, if we've got 1.5 amps in every part of this circuit, then that means there's 1.5 amps flowing through that bulb, 1.5 amps flowing through the middle bulb, and 1.5 amps flowing through the third bulb. This shows that our delta V predictions were correct, because if we do the delta V of any bulb, we see that it's going to be the current times the resistance of that bulb. And they all have the same current, they all have the same resistance, so all the bulbs will have the same delta V. But now let's go on to find the power dissipated by each bulb. To find that, we'll take the potential drop of each bulb and multiply it by the current. So it's going to be 1.5 times 1.5, and that's going to be the same for every bulb. So each bulb is going to dissipate 2.25 watts. So how do the brightnesses compare? They're all equally bright. Go ahead and make a prediction for yourself of what you think the brightnesses of the other bulbs will be. Will they be brighter than the bulbs that we had? And assuming that these are all matched bulbs with the same construction, then the power they dissipate will reflect the brightness of the bulbs. Do you think any of the bulbs will be brighter, the same brightness, or less bright? You can also predict what you think the potential values would be at different points in the circuit. Those are some important points there. And I'm going to go ahead and designate this negative terminal as 0 volts. When it comes to the final arrangement, you can pick your own points and label the potential values. Alright, so in this middle diagram, we see that we've got 3 1.5 volt cells all arranged in series. That's going to bring us up to a voltage of 4.5 right here. And if we keep going through more cells, we're going to get all the way up to 9 volts. How's that going to affect the brightness of the bulbs? Kirchhoff's loop law says that if we raise our potential up 9 volts, then somewhere else in the circuit we're going to have to lose those 9 volts. And I'm going to predict that we're going to lose 3 volts in this bulb, 3 volts in that bulb, and 3 volts in the third bulb. Batteries increase our voltage as we go from the negative to positive terminal, but bulbs and resistors will decrease our voltage here. Alright, if we create an equivalent circuit, we've got a 9 volt battery, and our equivalent resistance is again 3 ohms. So how many amps is it of current? Divide 9 by 3. We get 3 amps, double the current of what we had before. So we've got 3 amps here, 3 amps here, and 3 amps there. And just for completeness here, remember that our resistances of each bulb were 1 ohm. How much power is developed in each bulb? We've got to multiply the potential drop times the current. The potential drop is 3 volts. The current is 3 amps. So now the power dissipated is 9 watts. Much more than it was previously. This will be reflected in the brightness of the bulbs. Notice that when we doubled the voltage of the battery, the power dissipated by the bulbs was multiplied by a factor of 4. Now let's try the toughest one of all. I'm going to pick a few important points. we want to know what the voltage is at the negative and positive terminals of these batteries. I might also like to know what the voltage is at this point, and then perhaps right before the bulbs, and of course at these corners as well. I have to designate the 0. I'm gonna pick this negative terminal here to be 0. Okay. Now, because this battery's negative terminal is in contact with the other battery's negative terminal, this point and this point and this point are all at 0 volts. But as we go through the battery, using Kirchhoff's loop law, for example, even if we go through this middle loop here, that's an interesting one to analyze. We're going to go up 4.5 volts when we go the correct way through the battery. But when we go through a battery the opposite way, we're going to lose 4.5 volts. So we're going to get back to 0. But the only way that'll work out is if this point is also at 4.5 volts. And as you can tell, the positive plate of one battery is in contact with the positive plate of the other battery through a conducting wire here. So all of these points are at the same potential. So to answer the question, how do the brightnesses of these bulbs compare to the others? Interestingly, they are going to be the same brightness as the first diagram. We're going to lose 1.5 volts in this bulb. We'll lose 1.5 volts in the second bulb, and then we'll get back to 0 by losing 1.5 volts in the third bulb. To use Kirchhoff's loop law, we can start at any point of our choosing. I'll start right here on the negative terminal of the second battery. I'm going to go all the way around the loop, come back to the same point where I started. So we would gain 4.5 volts going through the battery from negative to positive. We'll lose 1.5 volts in our first bulb, lose 1.5 volts in the second bulb, and lose the remaining 1.5 volts in the third bulb, bringing us back to 0, and Kirchhoff's loop law is complete. When it comes to the power of the bulbs, they're going to be 2.25 watts each.